of the gauge symmetry, but a bit special part of the gauge symmetry, original gauge symmetry. Okay, so what is the gauge transformation? The gauge transformation is, of course, the change of the orientation of colored particles in color space, right? So, I mean, so intuitively, the fundamental quarks have one index corresponding to the orientation of color space, and so this orientation is changed by the gauge transformation. Okay, that is represented by this gauge transformation matrix V. Okay, and what? This is not 7, but 1. What is happening? Anyway. So, the adjoint representation is a sort of combination of two fundamental representations. So, you have two indices. Okay? And then one index is rotated by V, and the other one is rotated by V dagger, or V inverse. Okay? And so, let's think about the center of the gauge group. And what is center? Okay? Center is some terminology in the group theory. But anyway, the idea is very simple. Okay? The center is an element of some group, and that commute with all other elements in that group. Okay? So in the case of SUN, Zn elements are center. Okay? Zn is a center group of the SUN group. Okay? Why? Because if you consider the matrix like, yes, this one, okay? If you consider this matrix, this is proportional to unity, okay? But this is actually, this belongs to SUN group, okay? Because if you take the Hermite conjugate is of course the inverse of this matrix, right? And also, if you compute the determinant, then determinant is simply given by this zk to the nth power. And of course, zk is an element of Zn. If you multiply zk mc times, then you have 1. Okay? That is the definition of Zn. Okay? And actually, the explicit definition of this zk is given by this. So from this expression, it is obvious, right? If you multiply this quantity nc times, then what you have is exponential 2 pi ik, and k is an integer. So this is, of course, 1. Yes. So in this way, so this z is proportional to unity, and that means this can commute with anything. Okay, this is a trivial matrix, but nevertheless, this belongs to the SUN. Okay, and so this element forms one interesting subgroup of SUN, namely that is center group. Okay, and what is special about this center is following. Okay, for the adjoint representation, as I said, this gluon must be transformed by the combination of V and V inverse. Okay, so if this V is center element, okay, if this happens to be the center element of the center group, then the gluon is not changed at all. Okay, because of the combination of V and V dagger. But for quarks, of course, even center can non-trivially affect the quark, okay? Because only one V here. There is no V inverse. Okay? So the gluon is completely insensitive to the transformation belonging to the center group. Okay? And this is actually the center symmetry. Or more precisely speaking, the gauge transformation is written in this way, and at finite temperature, this gauge field must satisfy the periodic boundary condition, and after the gauge transformation, this A prime, the transformed gauge field, also satisfies the periodic boundary conditions. Otherwise, you cannot use the Matsubara formalism. Okay? And then, to satisfy this requirement, what is the properties expected to the this transformation matrix V? Okay? Of course, if V is periodic, then the transformed fields are periodic too. That is trivial. But that is too strong condition. Okay? If this is aperiodic, twisted by this center element. That is also fine because you have V and V dagger here, and so Z can be cancelled by one Z here and Z dagger here. Okay, and so this kind of transformation or the symmetry under this aperiodic gauge transformation. This is called center symmetry. Okay, so this is a bit complicated notion. Anyway, then the Polyakov loop is another parameter for this symmetry. Okay, so as I said, the Polyakov loop is given by this free energy difference. Okay, on the intuitive level, but in the field theory, you can define this same quantity in this way. Okay, why? Because as I said, the Polyakov loop is energy difference in the presence of single quark. And okay, and you know that in the gauge theory, the current and the gauge fields are conjugate variables, and so this interaction must appear as the A dot J always, okay, in the Lagrangian. And now you have test quark. That means this zeroth component, that is nothing but density. Density must have this delta function source, right? And then zeroth component of, sorry, the fourth component in Euclidean spacetime. Okay, this must be 4. Okay, the fourth component of gauge field should remain in the path integral, giving this phase factor. Okay, so this expectation value corresponds to the energy difference associated with the presence of this source, namely the test quark. Okay, and so this is so the Wilson line along the temporal direction or the force direction of the coordinator. Okay, from 0 to beta. Beta is 1 over t. Okay, from 0 to beta. So this Polyakov quantity needs a very complicated minimization that I will not explain in this lecture. But so actually the interpretation of a Polyakov loop is a bit tricky. And so, you know, as I said, so this can be interpreted in this way. But actually this single quark free energy, this quantity itself is not really doesn't have a strong meaning actually, because this quantity, the overall normalization, is easily affected by the normalization procedure, and so usually the consensus is that the expectation value of the Polyakov loop itself is not a physical quantity, okay, physical observable like energy or whatever. Okay, so the physical interpretation is very dangerous. So this interpretation I introduced just for an explanation, but just please don't take this interpretation too seriously. Okay, this single quark interpretation is a bit tricky. Okay, and so if you are interested in more details, I would recommend to see a very nice review article by Smilga in 1997. Okay, so he published a very nice review in physical physics reports. Okay. And oh, it's already almost 1 hour. Okay. So, as I said, this Polyakov group is order parameter for the center symmetry, and that you can see from this, the transformation properties of the Polyakov group. Okay. As I said, the center transformation is a gauge transformation satisfying this twisted boundary condition. Okay? And this twisted boundary condition, you can easily introduce that by introducing this twist at some point of the okay, at some point along the temporal direction. Okay? So if you have one winding configuration like this, so this is nothing but a Polyakov loop. Okay? If you have single winding, okay, this twisted boundary condition is introduced by changing the link variable at some point by this zk. So this quantity is multiplied by this zk. Okay? And so if you take the expectation value and if the symmetry is kept by the vacuum property, then this quantity and this quantity must be the same with some non-trivial factor here. That means if the vacuum is center symmetric, this expectation value must be 0, right? And so the center symmetric vacuum is confining vacuum having an infinitely large single quark excitation energy. Okay? And on the other hand, if you compute the Fourier correlation function, okay, the upward and downward configurations, then zk coming from this configuration and zk star coming from this configuration, and as a combination, this is actually the invariant under this transformation. Okay? And so, if you compute the Fourier correlation function, then this is something non-zero, or even in the confined phase where center symmetry is not broken. Okay? And in fact, this correlation function corresponds to the Wilson line expectation value, Wilson loop expectation value in the zero temperature system. Okay? Because at final temperature, the temporal direction is compactified, and so with this periodic boundary condition, this looks like two separate pieces. But if you expand this compactified manifold in this way, then this is nothing but the Wilson loop, right? So here. So this corresponds to the expectation value of the Wilson loop. And we know that in the confined phase, the Wilson loop expectation value should obey the so-called area law. Okay? And indeed, that is the case in the confined phase. And so this sigma is proportional to this area, okay? With some coefficient that is the swing tension. And so if this R is infinitely large, then naturally this correlation function must go to 0, okay? Because this part, this area is simply R times beta. Okay? So if R is infinitely large, this correlation function must go to 0. And so the Fourier loop expectation value, that is one part of this correlation function, that must be also 0, right? That is completely consistent with this intuitive explanation, right? Okay? So, actually, so the intuitive physics I explained on this slide is completely realized in this form in the field theoretical manner, okay? And in the confined phase, so this obeys the perimeter law, and so even for infinitely even for infinitely separated the correlation function, this goes to something non-zero, and so the Fourier loop expectation value is something non-zero too. Okay. And so the Fourier loop is the order parameter for deconfined. Okay. And actually, this is quite natural because in some sense, this Fourier loop can be interpreted as the SUN precession phase factor of a single quark inside of a Groniuk medium. Okay, so this is something like a AB phase. Okay, a Harold-Bohm phase in the presence of the gauge potential. Okay, and then so inside of the Groniuk medium, the static quark propagate into the temporal direction, picking up some phase factor in the presence of the gauge field background. Okay, and so this is the phase picked up by the single quark, and because the symmetry is not broken in the confined phase, this direction and this direction and this direction, three directions are equivalent. Okay, so they are equally picked up. And so, if you add three different directions, then this is naturally 0. Okay. So, in the confined phase, the quark excitation is projected out, okay, by the average of the phase factor picked up by the quark. Okay. And so, if you look at this order parameter behavior as a function of the temperature, this order parameter must be 0 up to some point. Okay, and then there is a phase transition corresponding to the deconfinement. Okay, and then this order parameter must take some finite value. Okay, and this is what you can expect for the pure Yamil series without forks. But full QCD has dynamical forks, and as I said, the center symmetry is explicitly broken by the presence of forks. Okay, that you can see from here. Okay. Well, as I said, so this property does not affect the boundary condition for gluons, because gluons have V and V delta. But quarks, for quarks, okay, quark is transformed by as a psi to V psi, okay, and so it is sensitive to the presence of this twist factor, okay. So if you have quarks, the center symmetry is explicitly broken by quarks, okay, and that means the order parameter must be something finite, okay, always finite, regardless of the state of the matter, okay. Even in the confined phase, or actually the confined phase itself is not really well defined if you put dynamical force. And that is actually the situation I explained using this slide. Okay, because of the string breaking, you cannot get clear characterization of confinement. Okay, and well, okay, so now. The 1 hour has passed, and okay, so here I want to explain about the part-additive calculation of the effective potential of this order parameter, but this needs some time, and so maybe today I should stop my discussion here. Okay, but anyway, so please remember that the Fourier loop is the order parameter. Okay, and tomorrow I will explain how to compute the order parameter of this, the effective potential of this order parameter, okay, to identify the phase transition. Okay, and actually recently there are lots of development in the measurement of the lattice propagators, and using this you can actually understand how the confinement deconfinement phase transition takes place in the field theoretical manner. And then, so you can actually estimate the phase transition temperature that is dynamically determined by the shape of this non-perturbative propagator. Okay, so that I will explain tomorrow. Okay, thank you very much.
Any question for? Okay. Can I try again to understand the possibility of having we'll define all the parameters for this transition Fourier. So my understanding is that when you have a Fermi system, and then you can expand the determinant.
Excuse me, expand what?
You can expand the Fermi determinant
Okay.
in the
Yes.
path integral.
Yes.
And then what happens is that you have this Fermi pocket moving around
Yes.
the world, come
Yes.
back, right?
Yes.
It's like moving around the torus,
Yes.
and then it comes back.
Yes.
And then that actually is the configuration that breaks the symmetry. Right?
So
Isn't that correct?
yeah, that
Otherwise, if
okay.
you just look at the action itself, I mean, without this kind of long range modes.
Yeah, of course. So you
Right.
can do the Hawking parameter expansion.
Right.
Then you can have many configurations. Some of them look like this, or like this, or you can have another type of configuration like this. Okay. Or I mean, for example, the bracket. Okay. Or Wilson loop is exactly so this. Okay. But if you have loop, then the situation is the same as this one. Okay. The upward going and downward going, the contributions cancel this center transformation, and so they are completely insensitive, and so only this type of configuration is sensitive to the explicit breaking of a center symmetry, and then you may think that there must be some projection to get rid of this kind of excitation.
That's exactly what
okay, that is possible.
Right.
Okay, but as I said, That projection procedure works fine for the finite size box. But you have to take the thermodynamic limit, and in that limit, that projection becomes very singular. Okay? The projection means you have to superimpose the many different orientations, right? I mean, for example, so so schematically, yeah, this type of the superposition you have to do, okay? And then the superposition results in 0, okay? And in this way, you can project out a single Cork excitation. But the point is that, okay, even though the weight factor here and here and here, they are equivalent, they are identical, the energy barrier between this state and this state becomes greater and greater if you go to an infinitely large volume, okay? And that means if the state falls into this point, for example, or this point, for example, then that state cannot go to another minimum, okay? And then completely locked in one minimum, and then the projection is removed in such a way dynamically. Or in other words, some unexpected Cork comes from the infinitely, the separated distance. If you take the infinitely large volume limit, okay.
So this is probably possible in the large N limit only, right?
Large N limit is different, okay. In the large N, the Cork loops are suppressed. And so the phase transition becomes well defined. That actually I will mention tomorrow. That is a case. Yes.
You mentioned the variable loop depends on renormalization scheme.
Yes.
Is that just up to a strong coupling constant? If you multiply strong coupling constant to the variable loop, is this quantity does it still run?
Strong coupling constant in G?
Yeah.
No. It comes from the okay. So it's no. So well, what to say?
For example, in this in the first line, is the quantity phi? Does it depend on the
you mean
renormalization
this
scale?
G? Yeah.
Yeah.
No. It comes from the self-energy contribution. Like okay, the variable loop is this kind of configuration, right? And then you can have many diagrams, like so this guy or this guy, or so more complicated diagrams. Okay, so they give